Okay, so recording should be started, so we can start. Yes, I guess today we have Lisa, who is a PhD at Stanford with Clark Barrett, and also spent the summer as an intern at Gadwa. He's going to be talking to us about automated lean proofs for every type, and some of the very exciting work, and I think very widely applicable work that she's been doing in this context, which I think was mainly done over the summer at Gadwa. And so, yeah, floor is yours.
Thank you. So I have about 35 minutes of content, so please feel free to interrupt me. And I also can't really see the Google meeting, so yeah, just feel free to speak up if anything is unclear. But as Alex mentioned, I'm currently a PhD student at Stanford. I also work on the SMT solver CBC5, and this is work that was done at GatWav with James Parker, Valentine Robert, Ben Hamlet, Benoit Razid, and Brad Decker. So with that, let's start. So my PhD is in verifying cryptographic systems, specifically verifying cryptographic systems using SMT solver. So pretty much when I talk about this, I think of a pipeline where we have an algorithm implementation. We give it to some verifier, which could be SAW developed by Galois, maybe Picus developed by Veridize, or maybe it's an interactive fear improver like Daphne or Lean. And then we're going to give it to an SMT solver. Hopefully CBC5, not Z3, but any SMT solver you prefer. And in this pipeline, I specifically focus on the SMT solver, the encoding to the SMT solver, and so far specifically zero-knowledge proof circuits, which is what we all focus on. So overall, we all have a common goal if we want to automate verifying zero-knowledge proof virtual machines. And we want to do this using SMT solvers, since so far AI is not really good at writing formal proofs. But one of the issues that arises is when we say automate verifying zero-knowledge virtual machines, this is a little bit of an umbrella term, especially if we look at this from the SMT queries. So depending on what you're trying to verify, the SMT queries can be completely different. And as a result, while there has been a lot of new novel developments in this area in terms of decision procedures, they're not applicable to every use case. So some of the use cases are the different property that you're trying to verify about the zero-knowledge proof. For example, you might be verifying the determinism of a circuit. You might be verifying the completeness and soundness of the encoding from the bit vectors to the finite fields, or maybe the agreement and consistency of witness generation. Further, the circuits are all very, very different. They might have nonlinear multiplication, they might have decomposition to bits, or they might have field inverses. And depending on which aspects you have, you might want to use a different SMT decision procedure. And last but not least, there's also the tool level diversity. So you might be using an interactive fear improver, or you might be using symbolic execution. And depending on this, the support that currently exists for SMT solvers is vastly different. And so as we're trying to generalize this whole system, it's important to consider that the SMT decision procedures will also need to be generalized, or we will need a way of deciding which one to use. And so this summer at Galois, the specific question that we attended to answer is, as we move towards the lean theory of everything, as my advisor likes to call it, can we actually use SMT solvers for zero-knowledge virtual machine verification lean? And our answer was not out of the box, but possibly with new tactics. And so what we did is we created a novel tactic for zero-knowledge virtual machine encoding. I hear a ping. Does that mean anything?
I was telling people to leave questions in the chat for after to not interrupt the talk. Sorry.
That sounds good. Yeah, I cannot see the questions, so if anything is super unclear, please feel free to interrupt. But yeah. Okay, I'll continue. So it's a novel. So we created a novel tactic that we call Bitmodiq. And so for the remainder of this talk, I first want to give an overview, which will include the problem that we focused on, which was specifically the JOLT lookup tables. So these tables equate bit vector instructions with finite field operations. Then I will talk about existing SMT decision procedures and why they did not apply to our problem. Then I'll talk about existing SMT and lean bridges and why they also did not apply to our problem. And then I'll finally introduce our tactic. I'll talk about some of the theory behind it, and then give a mini tutorial so then hopefully you can also use it in your project. So let's begin with our problem. So the way JOLT zero-knowledge virtual machine lookup tables work is they have some elements that are bit vectors. So for this example, it's going to be BV1 and BV2. And then they have finite field elements that are going to represent every bit in the bit vector. So in order to equate this equation, we do the finite field to bit vector conversion. And you could do the conversion the other way around, the finite, like bit vector to finite field, but this is just simpler for the JOLT encoding. And so our bit vectors are W length, which is a parameter, and in reality, it's either 32 or 64. And then we do the multiplication by 2 to the I to move every finite field element bit into its correct place. And then we also do the multiplication of xi times xi minus 1, and similar for the second bit vector. And so this is done because, as you know, finite fields don't have inequalities, so we have to do polynomial multiplications. Fun fact, these are actually super slow for the SMT solver. And last but not least, what we're actually trying to verify is going to be some bit vector expression. So in this case, it's going to be an XOR, and then we're going to have a polynomial that is going to simulate the XOR in the finite fields case. So in this situation, we're going to XOR all the bits together, and then we're going to use a 2 to the I in order to move this bit into the correct location. And so with that, let's continue. Now we have our problem. As an SMT solver developer, after I have my problem, the first step that I try to do is I try to choose the correct SMT theory and decision procedure. And this is super important because if you choose the wrong theory or decision procedure, as you know, the SMT solver can run forever. So in our problem, we have finite field elements and bit vectors. And there are a couple of natural ways of representing this problem in SMT, actually about 4. So the first one that we're going to look at is using nonlinear integer arithmetic, which is what is often used in practice. The issue here, and so we can encode everything using mods, using an in-blasting procedure. What the in-blasting procedure does is it lifts from, I guess maybe lower since it's a lower mod, but it's going to take bit vectors and then it's going to lift them to the integers by adding mod 2 to the w. And so this, and they also have specific passes to work on XORs or specifically bit vector operations. And so this is fine. That's why we all have everything in one theory. But the issue here is that the way the QFNIA procedure works is it introduces auxiliary variables for each modulo operation, which is very slow. Because if we look at our polynomial on the previous slide, we have a bunch of multiplications. So every multiplication is going to have a modulo operator, and this is going to kill performance. The next approach is to use the theory of bit vectors. And so this is going to use very large prime. It's going to encode the large primes that are present in JOLT verification and all cryptographic verification using very large bit vectors, which is already a problem. In addition, in order to simulate the modulo operations, modulo prime, we have to use something called BVRM, which actually converts your expression back to the integers and then back to the bit vectors, which is extremely slow and is also going to kill our performance. So next is the finite field theory, which was developed by Alex Ozdemir in 2023, who's used to be my lab member, now professor at Georgia Tech. So there is a problem here that the theory has fundamental syntactic restrictions, where we cannot encode variables that exist modulo more than one prime. However, we can use theory combination. So if we encode our finite fields into field elements and then keep the bit vectors as bit vectors and use a procedure called theory combination to exchange information between the two, this could potentially solve our problem, although theory combination is known to be extremely slow. And so last but not least, we also have the mod range solver procedure, which I designed with Veridize last year and was published at CAF 2025. And here we could encode everything using mods with in-blasting. And how this decision procedure works is it does not establish a common basis. Instead, it lifts and lowers between the moduluses and the integers, and then runs a Grosvenor basis in each of the separate sections. So as a result, we're able to avoid some of the overhead that happens when we establish a common basis. Okay, so we have 2 possible solutions of using finite fields or maybe using this decision procedure that I built. So now let's look at it specifically in Lean. And let's start with my decision procedure because, you know, I built it, so I want to use it. So what we're going to do is we're going to use in-blasting on the bit vector side. And then we can run my decision procedure. And great, you know, this was specifically built for these kind of use cases. So we're done. The issue is we're not actually done because we're working in Lean. And so there becomes a lot more overhead on what type of SMT decision procedures we can use. First, they need to have proofs, which in-blasting does have, but integer reasoning, which is my procedure, does not. Second, these proofs need to be translated to Lean. So Lean needs to know how to interpret them. And neither in-blasting nor integer reasoning has the proof translated to Lean. Further, the Lean types need to actually be translated to Lean. And so currently, SMT lib does support the translation from integers to SMT, but it does not support the translation from bit vectors to SMT. So seems like there's a lot of excess, can't really use it out straight out the box. And further, there's also the question of how do we translate finite fields to integers, which theoretically should be simple because we could just add mods. But once again, since we're operating in Lean, there's nothing that can do this for us automatically. Okay, we're not done. Let's look at using the theory combination, the finite field approach. So here we're going to use the bit vector procedure, and then the finite field procedure by Alex Ozdemir, and then we're going to use theory combination. So what is the support for Lean in this? The support is a little better. Bit vectors do have proofs, and finite fields currently have proofs that are in progress. And this is work done by both the CBC5 team and also by Nevermind. Then bit vectors proofs are not translated to Lean, and while there's ongoing work, it is not close to being done. There are finite fields proof translated to Lean. As I said, bit vectors are not currently supported in Lean, the translation from Lean to SMT. And then the finite fields, there's ongoing work. And then theory combination, we do have proofs. And there's no, the others do not apply since it would just equate the two. So this story is a little better. We still have some X's, but maybe there's some hope. Except theory combination is known to be extremely slow. So anytime you're running two theories, you're losing a lot of information in your SMT decision procedure, because what's going to happen is you're going to have one theory that's going to do its decision procedure, and then it's going to communicate this its solution to another theory. And then, so pretty much you have a lot of blockers of single variable assignments, which just does not scale well in practice. And then if we look at our problem from a larger scale, is this even the right approach? When we're dealing with jolts, we have a lot of xi and yi, which are simulating bits, but there's not actually any finite field reasoning. There's no inverses. So as a result, do we even need something as heavy as a Grosvenor basis, which is included in both the finite field decision procedure and in my decision procedure? And so, when you're really stuck, what you want to do is you want to look at the bigger picture. So let's look, we have Lean on one side, and on the other side, we have SMT. And both Lean and SMT have its own types. So in Lean, you can have Z-mods, integers, bit vectors, fins, nats. And in SMT, you have a smaller, but still very rich type system of finite field elements, integers, bit vectors, bools. And some of the translations between the two are very natural. So Z-mods to finite field elements, ints to ints. But then others are a little more complex. For example, fins. Do we want to use bounded integers? Do we want to use bit vectors? Similarly, for uint16, is a bit vector better? Is an integer better? Unsure. And so as I said, there's a lot of work of building a bridge between those two, but it's currently incomplete. So the two main bridges that I know of are AutoSMT, which is developed by Yi Chang, who is one of my lab members. And what it does, it converts the most prominent Lean types, so this would be integers, bit vectors, to SMT types. So it actually does not have support for finite field elements, but it would be able to transform Z-mods to integers, but then it would add a lot of overhead of additional axioms in order to talk about the modulus, which are actually going to overload our solver. And similarly, there's also Lean SMT, which is a bridge the other way. So what it does, and it's actually also built by one of my lab members, but what it does, it transforms the proofs of the SMT back to Lean by understanding every step that the SMT solver takes. And so once again, it has support for non-interpreted functions. It's currently working on nonlinear integer support, but it does not support every functionality. But if we look at this, we really are relying on these two people to translate all of the Lean types into SMT, and we're also giving them a lot of power of choice. Whereas in reality, it's really the developer who knows their program best, meaning it's really the developer that knows which Lean type is simulating which SMT type. So our proposal is that we need more translations between the Lean types themselves. So for example, in our case scenario, we were using Z-mods to simulate bit vectors. So a possible solution is to translate Z-mods to bit vectors and then use SMT, which would be the natural decision procedure that we actually want to use in this case scenario. And so that brings us to the second part of our talk, discussing the novel Lean tactic binModQ that we built. So what this tactic does, it translates Z-mods to bit vectors. So we take a Z-mod, then we translate it to nat, since this is the underlying type of the Z-mod infrastructure, and then we translate it to bit vectors. And then we're going to use BV_decide, which is a SMT tactic that is built in Lean. So it's very similar to Bitbootla, except everything is actually built in Lean, and it's built by Tobias Grosser's group, I believe. And so my first attempt at doing the XOR proof that I show the XOR function equality that I showed you earlier in the presentation was about 213 lines, and it took me about 10 hours. Granted, I was not really good at using Lean at that point. Nonetheless, XOR is one of the simplest instructions that Jolt uses. And now we can just do it using one-line tactic, solve MLE, which does a translation and then discharges to BV decide in about 10 seconds. So if we do a rough estimate of the amount of work, there are about 32 Jolt tables if you take those from Jolt, the original paper, and also the Twist and Shout paper. So we saved about 6,816 lines of code and also about 320 hours of manual proofwriting. And the story is actually more complex than this because these 6,816 lines will have to be maintained, meaning that all the different functions that we use, all the different lemmas, if Lean decides to update mathlib, somebody will have to manually go in and fix those. While right now it is just a tactic. So if something decides to upgrade, all we have to do is we have to maintain the tactic, not the proofs themselves, which is much easier. And so with that, let me explain to you how this tactic works. So there are two main challenges that we have to solve when solving this tactic. First, when you're converting from Zmod to Nat, you have to show that your expression is less than the field, which is actually fairly easy to do because the field is so big. Then you also have to show that all intermediary values are greater than or equal to 0. So this is true since we are simulating bit vector instructions. However, it's not exactly obvious since we do have minuses. It's just for every minus, we're also going to have a plus, if that makes sense. So 2 is a difficult challenge. And then similarly, when we're translating from Nat to bit vectors, we want to show that the expression is less than 2 to the W. And we also want to show that all intermediate values are greater than or equal to 0. So now 4 becomes easy since NAD by definition is going to be greater than or equal to 0. But 3 is the difficult part since sometimes for efficiency, we want the size of the bit vectors to be as small as possible. So we really have to be really careful with our bounds analysis. And so I'm going to talk about 3 on the next slide. And if you're curious about 2, feel free to ask offline. It's fairly a similar methodology as 3. And so let's say we want to show that our expression is less than 2 to the W. So let's go back to our motivating example of XOR. So what we're going to do is the first naive solution that we can do is we can approach it using the Lean way, right? So we can traverse our AC using existing less than or equal Lean lemmas, and then do a range analysis this way. But what happens is that Lean lemmas do not take account variable dependencies. So meaning what it's going to do, it's going to apply the natural range analysis rule, meaning, for example, when you do addition, the addition of 2 things must be less than or equal to the addition of each of the variables. So a plus b is less than m, is transferable to a is less than n, b is less than c, and then the result is n plus c is less than or equal to m, right? So if we look at our XOR, what it's going to do, it's going to replace the upper bound of each of the variable by 1. Which as a result is actually going to lead to overflow. And we're going to not be able to show that our solution is less than 2 to the W, where W is the smallest size that we could fit it in. Okay, so we can do a second solution. Since X and Y are bits, we can do case-by-case analysis, meaning we can look at every bit operation and then see that, oh, here's a variable dependency. This is going to be less than 2 to the W. However, the issue here is that we have 32 or even 64 bits. So if we actually do a case-by-case analysis of every case, and we take at least a second for every case, it's going to run longer than my lifespan, much less than my summer at Galois. So this solution is also not scalable with large W. So that brings us to the real solution that we used, which we did hybrid. So we used both what we would do in an Lean and also what we would do in SMT, where we traverse the expression, and we also used bit-by-case analysis. And what we did is we applied less than or equal to lemmas until we reached expression with 2 variables and subtraction, and then we did case splits. And so as a result, we only had about 4 cases for each of the, addition of for each 2 to the I we had to consider. And so this was a lot more scalable as opposed to trying each case possible. And that brings me to the comparison with theory combination. So as I mentioned before, theory combination currently does not have proofs, So this is just me manually sampling 10 jolt files and then translating them to SMT, where I kept the bit vectors and the finite fields and then established relationships between them. And this graph is a cactus plot, which is very common in SMT community. So you want to be in the lower right corner. On the bottom, you have numbers of instances solved, and then the top you have time. So you want to solve as many instances as possible in the least amount of time. And as you can see, SMT actually only solves one benchmark in 3 minutes. On all the other ones, it times out, while we are able to solve all 10 in under 3 minutes. So I believe it's about 2.5 minutes, which is really, really great. And the benchmark that SMT does super well on is greatest bit benchmark. So all it does is just extracts the greatest bit out of the polynomial. So I believe there's some simplification that's going on that makes it super fast. But if you look at this table, it's actually crazy results because SMT is built in very optimized C++ code, while Lean is fairly slower than C++. And so the fact that we're doing better just shows the importance of choosing the right decision procedure for your problem. And so I'm going to give a little demo to show you how it works. So also some of the definitions are still work in progress. Also, hopefully it'll stop being super blurry. Great. So this is an example of the AND table in the Jolt Zero Knowledge Virtual Machine Verification. I used AND because it's a little bit faster than XOR, and I didn't want to waste your time. So what we're going to do is we're first going to import the definitions. So the definitions defines the prime and also imports the bitmod tactic. Then we have to set heartbeats to be really big because this tactic does take at least a couple, or maybe at least half a minute. Then we define our table, which we can see has 64 bits. So it's over 32 bit vectors. And then it has some multiplication where it inserts the addition bits into the right location. And then the way we chose to currently define jolt is we are equating every bit in the bit vector to a bit in the finite field. This is not actually required for the tactic to work, but this is just how we chose to define jolt. And so as you can see, there's a lot of bits. And so now we're going to equate the AND output to the polynomial that you saw earlier in the finite field. Then we unfold all the jolt specific constraints. And then we run the solve MLE tactic where we pass in the vector size that we're verifying, which was 32. And so now we're going to run. It takes about 20 seconds. So I'm going to waste 20 seconds of your lifetime as we wait for this to finish. But the fun fact is the equivalent SMT lib runs forever. So the fact that we're able to finish in 20 seconds, as I said earlier, is very impressive. And so it's done. As I said, it's 20 seconds, 18 seconds, you can trust me on that. And then it also outputs the final range analysis that it did, which was the substitution using the lean lemmas for this specific analysis, since there's no subtraction, so no variable dependencies. So that's how it works. And then I believe I have another question.
Yeah, so I was wondering how well does it scale with the size of the the size of the vector? Like if you change it from 64 to 128, as Jolt has moved to 128 now, then does it still run in a reasonable time?
I ran a couple of experiments. I've not tried all the tables. So our bottleneck is BB decide, not the range analysis that we do. It does. I mean, I believe with 128, one of the issues is also just compiling the lean file itself with the polynomial table, which already takes a long time. But I would expect it to scale okay, if that's the answer. Well, that's the answer for you, I guess.
Yeah, thank you.
And again, I would expect it to scale better than the other techniques that are currently in play, but there are limitations of bit blasting. So it is possible that some of the more complex instructions, like PEXT, for example, it would not be able to do. And so next question is, how do you use it in your own project? So in reality, I showed you that it was one tactic, but in reality, it's 3 different tactics with a lot of, I guess, boilerplate code that solve MLE hides. So there's the first tactic, which is valify, which translates from zmod to nat and takes care of the fact that all the expressions have to be greater than or equal to 0, so we can't have negatives. And then there's bvfi, which is going to translate from nat to the bit vectors. And these two tactics introduce two goals into our context. So it introduces the fact that our expression has to be less than our field, and then it also has to be less than 2 to the w, which is what we have left to prove. And so then we have a third tactic, which does the range analysis that I talked about earlier. And so it's called try-apply lemmas and hips, so the hypotheses that are in your context. And so after this, you can run bv-decide, which is not a tactic that we built, and then your problem is solved. And the things that we require proofs that your field is prime, that your field is not equal to 0, and that your field is greater than 2. So these are not proofs that we do for you, but proofs that we expect to have, and that are required for lemmas to use. So we've been working on generalizing it to the CIRC compiler. This is a shared compiler infrastructure for compiling to constraint representations, and it's built by Alex Ozdemir. And so what it does is it takes zero knowledge proof it takes first fives and translates it to finite fields. And it also does some ILP translation too. And the very interesting part about it is it has a finite field blasting step that was verified using SMT in 2023, but they ran into a scalability issue. So they stopped at 4 arguments with 4-bit vectors. And I believe this took them, which is about 16 bits, and this took them about 30 minutes to prove. So we think we can do better, and we're currently working on generalizing the tactic to work on this. So I have another small demo on how we would use it on CIRC. So what we do is first you're going to define your field. So here it's a large bit field, and then also the zmod f. And then you're going to define your variables. And then you're going to prove that your field is prime, so the facts that I talked about earlier. And I was too lazy to do that. So we have a couple apologies. And then you are going to you're going to define your lemma. So this is an example that CIRC currently discharges to the SMT. Pretty much I just manually rewrote this in Lean, but ideally we would capture it and rewrite it ourselves. And so what happens here is we have our polynomials of the fact that x squared is equal to x, which is defining the fact that x has to be a bit. And so this is done for 0, 1, 2, and 3. And then we have our addition, where we are placing the bits in the correct location for the multiplication of the 2 bit vectors of a and b. And in this example, there are 2 bits, but we're hoping to scale to as big as 16. And then our verification condition is currently intermediary. So all CIRC is checking is that the first bit is equivalent to the 0th bit of the finite field. And in reality, I believe they also are going to be checking the second bit, but they don't check all of the bits because all of the bits don't matter to them. They only care about the actual bit vector size. And so step 3 is a tactic requires you to have necessary bounds conditions on all of the variables. It's okay if some variables don't have bounds, but the specific use case that we're trying to emulate is where all the variables have bounds. Then so this is a translation lemma that we proved, which translates the polynomial multiplication into the bounds that are necessary. So we want a bound on the x val, which is the natural number representation of the finite field element, and we also want the equivalent in bit vectors. So it's an or, but it could also be a bound. Both are fine. And this is a lemma that we provide currently, but we're also curious about, depending on your constraints, either as we're working to generalize, hopefully this is something that's going to generalize to other projects, or maybe somebody will have to write an additional lemma. And so then we rewrite all of our hypotheses to be what we want. We unfold all of the vector definitions. Then we're going to turn the zmods to natural numbers. So we do injectivity on adding the zmod to both a hypothesis and the goal. And then we're going to use valify to prove that everything is greater than or equal to 0, and also introduce the modulo operator in the field. Then we're going to eliminate mods. Then we're going to turn the natural numbers to bit vectors. And so this is a similar step as went too fast. This is a similar step as using the Zmod to nat, where all you're doing is you're adding an injectivity lemma, and then you're running bbphi to translate. And both bbphi and validphi requires you to pass hypotheses. And it's okay to pass hypotheses that are not needed. We pretty much just need the bounds on the natural number variables that we require. And then last but not least, we're going to run bbdecide. And then once again, we're going to run try-apply lemma hips, which also requires you to pass all the hypotheses in your context on all of the variables. And if you don't do this, you will just have to manually apply the hypothesis. So the lemma is going to finish early. And then we're going to exit, and we're going to run our lemma. And so this one is pretty fast since it's not a lot of bits. So the sorries are coming from the lack of proofs for the field primes. And as you can see, we were able to solve everything in about 2 seconds. Great. So in conclusion, we showed that bit blasting is possible and even efficient for zero-knowledge virtual machine encoding verification. So as you mentioned, there is a chance it might not work for extremely big bit sizes, but nonetheless, it works so much better than Fourier combination, which was the previous state of the art. We presented a novel tactic in Lean that translates from Zmod to bit vectors. We believe that type translation will be essential for using SMT and Lean in the future, as the Lean to SMT translation cannot possibly do every type, and it is very difficult for SMT solver to infer what types you're actually simulating in your problem. And we're currently searching for more benchmarks to generalize the workflow of Bitmoda queue. So if you think that your project might be a good fit, please reach out, and hopefully this will make the tactic more generalizable and easier to use in the future. And this is the tactic to be integrated. And I know earlier, I've often said that my decision procedure will be integrated in CVC5, and we're still working on that, but I believe this is more likely to happen sooner. And with that, thank you so much. Are there any questions?
Yeah, does anyone have a question? And then if everyone has a question, just, I guess, unmute and ask it.
Yes, yeah.
Otherwise, I'll have some.
Thanks for the presentation. I was wondering if you think it can apply to other kind of ZKVM, as Jolt is using a lot of lookups, as I understand. Do you think it works well with the other kind?
So I think anywhere you have you have bit vectors and finite fields, it should work fairly well. So the main aspect that we're targeting in this is the simulation of bit vector operations in fields, if that makes sense. So for example, if you're just verifying the determinism of your circuit, where it's just finite fields, I don't think this is going to work very well. And I think the finite field decision procedure is going to be much better for that use case. Hopefully that answers your questions. Let me know if it doesn't.
Hey, Lisa, I joined a little late. This is Shankara. Did you do this for, what bit sizes do you use? Is it 31, something like that?
So currently in Jolt, we use 32, so 2 bit vectors size 32. We're hoping to scale it to 64. I have not run a lot of those experiments just yet. Yeah. So I believe previously in CIRCE, they could only go up to 16.
Hey, thank you for the presentation. Yeah, one question on my side, because once like Shankara, I joined a bit late and also had some bad internet at some points, which is you made some comments on the performance of the sort of like the lean tactics versus sort of SMT implementations. And as you know, we've been working on certainly sort of doing proof reconstruction from the finite field decision procedure that Alex Ozdemir embedded into CVC5, and we also got some, shall we say, surprising performance outcomes in the sense that, like, for example, at least for the moment, and we're still working on optimizing, but at least for sort of like reasonably small examples, the Grind's Grubner basis solver is like much faster than calling out the Cocoalib and then reconstructing the proof for the moment, at least for 4 small examples. And so I'm sort of curious to go over that again. So you have solved what's on the x-axis here, sorry?
Yeah, so solved instances on the x-axis and then time is on the y-axis. So thank you for your question. I think this is something that is very much understudied. So the issue is you're doing the SMT, so you're running CBC5 and then you're converting the proof, the time it takes to convert the proof is still very, very important, right? So even though the SMT solver in Lean in C++ is faster, it might take your time to convert it. Whereas for like smaller things, as one example is like BV Decide, it runs specifically just in Lean, so there's no conversion that's needed. Here, we're not even converting the SMT proofs, we're just running SMT and comparing it straight up. And the issue that here we're talking about is the fact that when you use Fury combination, this is not the right approach for this problem. What you want to do is you want to convert to bit vectors because you're simulating bit vector arithmetic. But I think your problem is also very interesting of the question of when do you actually need something as heavy as an SMT solver, and when is the time done to do computation in CBC5 is worth it. There's also
exactly.
Yeah, and when
sorry, go ahead.
I was just going to say, when the SMT solver does the proof trace, there's also some work that can be done on which computation can be done or can be given to Lean. So then the Lean is a little faster. So I've been working a little bit with Pedro on it, but I would be very curious to hear your thoughts.
So as I said, on our end, I mean, for the moment, the reconstruction, I think, is suboptimal in the sense that I think there's a little bit more information that we could extract from CVC5 to not have to use automation on certain steps to extract certain information. But yeah, I mean, so František and Fabrizio, who are on this call, actually did the work on this project, so might have some better or more interesting commentary than me on this. If you guys don't mind me throwing you under the bus, perhaps František.
No, yeah, it's fine. Yeah.
Fabrizio, go ahead, Fabrizio.
Yeah, one step that we are having a lot of difficulties is just relate our polynomials with what CVC is using. One thing that Daniel thinks will solve a lot of our problems if we are able to track the rewrites that CVC5 does internally. And I think it's something that Pedro is doing. But right now, what we will do, because we start from an initial set of polynomials, but when we send it to CVC5, CVC5 does slightly modifications to it. So we have to keep this tracking a lot, just calling some automation to know that we are in the right track. But if we have access to the rewrites, I think that it will be a lot faster than what we are doing right now.
Yeah.
Hi, this is Peter, also from Nethermind. I have a question related to the initial slide where you described how XOR is defined in terms of finite fields, but also I was curious. Yes, that sum, but also I was curious about have you verified anything that's not like bit by bit separable, like sort of addition, multiplication, any like functional correctness of operations like that?
So not
yes, this is the sum that I was talking
this
about.
slide. Yeah, not yet. I expect we're gonna run into some in Circe. Like I said, the specific target that we were focusing on is bit vector to finite fields, and most of those, often from my understanding, use the conversion to bits and only has maybe like 2 or 1 vectors of finite fields.
Yeah.
There's also, like, specifically for Circe, this is usually the witness, and often this is already computed for the compiler in case of soundness. So there's a way to avoid needing it. Sorry, short answer, no, we have not. I would expect it's going to slow performance a little bit because, as we said, it's kind of fairly well known that bit blasting is usually not really good if you have a lot of...
Yes.
I guess I would actually say, well, Lisa has verified all the lasso lookup tables. So this is like all of Jolt's instructions. So it is emulating the whole RISC-V machine, right?
Yeah.
Like additions, multiplications, like all this.
I'm also just curious there to see in that FF to BV, is the expression that function takes supposed to be in the finite field?
Yes. Yeah. So all of these operations are in the finite field.
But will that not overflow? For example, if you're baby bear and you're 32-bit, that will overflow.
Yes.
So Jolt uses BN254.
Which is how high?
250 bits.
Oh, okay. So you're just there's no overflow on that of that kind.
No, yeah, we don't have to worry about it here.
But that's interesting. But what happens if you do need to worry?
I would love to. I don't actually know any examples where there is overflow. As I said,
So, for example, succinct uses 60. So, like succinct uses like in any zkVM that uses a prime that is less than the width that the zkVM is supporting. For example, Baby Bear in 32-bit and 64-bit, Koala Bear in 32-bit and 64-bit.
Yeah, then you would have to keep at least one of the mods. So what I believe you can do is when translating to the vectors is add BB room. I believe if you only have one, it should be better than having one for every operator, right? And this would still, this would be like something we would have to add to this tactic to do this.
Okay.
It would be better. It would not be great.
Also wanted to add that the jolt instructions are not in one-to-one correspondence with RISC-V instructions. It is a non-overlapping thing because some RISC-V instructions get decomposed into a series of jolt instructions. What determines a jolt instruction is just that whether it has a nice MLE or formula. And so Jolt also defines some other sort of virtual instructions that are not part of RISC-V, but are helpful in this decomposition process. So something like division and remainder in RISC-V are broken down into a series of more primitive Jolt instructions.
Mm-hmm. Yeah, that's a good point. So I guess we verified all the MLEs for Jolt. But those did have some very, like I said, they had a PEX. They had some very complex arithmetic.
Okay, any other questions from anyone else?
Yeah, I was wondering if you tried other solvers like Z3.
Z3 does not have finite fields, so it would not be comparable. And then before, so the project that we did with Theridize, Z3 was a little better for nonlinear integer arithmetic for those specific problems. But again, when we're going to do the conversion to moduluses, adding a mod, like the naive encoding would add a mod for every operation, would just not work.
So I have one quick question. So I think one question was actually around performance.
Mm-hmm.
And where do you think maybe there's actually even more juice to squeeze out of just optimizing your tactic and the actual the underlying lead code for that tactic? And then I have a second question maybe related to this as well, which is whether you see any other potential tactics that in this way would kind of replace our need to call out to SMT solvers in ways which don't always work and which can be slow or misperformant or have series combination, which then breaks down. It would be interesting to see if there's other things we should be looking at.
So I had shout out to Val who looked at my code a lot this summer and really helped me like make some of the things faster. One of the optimizations that we do in Solve MLE is we don't want to prove that it is less than 2 to the W and less than 2 to the field. We just do 1. So we don't have to do both of those in range analysis, which is a lot faster. Whereas right now for Cersei, for example, we're going to do it twice because we don't have that optimization naturally. So as we generalize it, hopefully we keep that optimization. But really the bottleneck in this decision procedure is BV decide. So the bit blasting part that is slow. I believe Tobias and his group are working on making it faster. There's also like my group, which works on the Bitbootslum SMT solver, are currently submitting some paper to TACAs on a novel optimization. So potentially investigating whether using BV decide or using the SMT to lean bridge and then converting the proof is faster could be an interesting optimization. But other than that, I don't currently see a lot of easy or low-hanging fruits for optimizing this tactic. And then your second question was about more tactics. So I think the tactic that Nevermind is working on is very important, and also about Haniel and Pedro's on the using finite fields explicitly, because like we talked about, there are cases where there are no bit vectors, and then this tactic just does not make sense to do. And we do want to use Grosvenor bases and the simulating the inverses further. So SMT solvers are good to use when there's conjunctions and disjunctions. So also investigating on when do we want to use grind and their Grosvenor basis versus when do we want to use SMT solver, I think is interesting. Hopefully that kind of answers your questions. Oh, and then also doing the translations with BVRM. So in cases when there's no overflow, seeing if we can, even if we keep one modulus, is it still efficient, would be interesting. Sorry, that was a long way of answering your question. Hopefully that answers it fully.
Yeah. I think that's super interesting. I think, like you referred to as a start now, there's maybe a vibe of a kind of lean theory of everything. And so it's interesting to think about, I think, not how to replace other things, but how to make as good use as we can of SMT solvers and the existing decision procedures in SMT solvers. I think, because one thing that comes up as well is obviously one of the nice features of trying to prove things in lean is that even within a single proof, it's much easier to actually split off cases where you want to call two different SMT procedures, which also works as a nice way of working around the series combination issue. That you can just do kind of a bit of a split or some kind of case analysis within a single proof, and then call out the same SMT solver but to different actual series.
Yeah, I very much agree. Like, you kind of are the user, so you have the ability of interactivity, so you can kind of know maybe what theory you want to use, which makes it easier, as opposed to just using symbolic execution where you're stuck in one translation that is done for you.
Yeah, and so with that in mind as well, do you see it going, potentially the other way around? Because obviously we have a bridge from lean to SMT solvers and from SMT solvers to lean, and we also have some sense of how to generate proof obligations in lean, and we do this, when we're extracting Rust to lean or something like this. And I mean, is there some sense that you could take something that SMT solver is struggling with, export it to lean from the SMT solver, have potentially some automated split in lean into domain-specific things which call out to a single SMT series, and then feed it back to the SMT solver, kind of fully automatic end-to-end interaction between both to make the SMT solver's job a bit easier? Because it seems like a lot of SMT-based tools, the magic in them is not so much generalizing SMT solver, which everyone has access to, but then a lot of the pre-processing and case analysis that happens before things are offloaded to the SMT solver, or even just performance issues like managing, memory and things like this. And it seems like potentially lean and tactics in lean could serve as a nice way to interact with SMT solvers and help them find sub goals which are tractable with single series.
That would be really, really interesting. I think it would really depend on the decision procedure that you're using, because one example is QFNIA actually works. It uses simplex under the hood, and so it actually very much like it gets rid of all equalities, all disequalities, and then it introduces a lot of branches. So it's gonna overflow your context with just too many lemmas that it learned. That will it overwhelms me when I look at the SMT traces. It's gonna overwhelm anybody who is doing the lean proof. But I think the possibility of SMT being like, oh, I'm struggling on this, can you help me, would make it very, very interesting and a lot more interactive, especially because like in SMT often, one of the reasons why parallel SMT works really difficult is the fact that there's often a part of your search space that is just really difficult. And so as you prune around it, you still have this very difficult search space that is hard to do. So bringing this back to the user would be super interesting. But I think Amazon maybe was doing something. No, actually, I don't know of a single project that is currently working on. So it would be very cool to see.
Yeah, definitely. Okay, I guess last chance for questions for anyone who's interested, and then otherwise we'll stop the recording and wrap it up so that everyone leaves on time.
And anyone has any questions afterwards, please feel free to email me, or would love to continue talking about this.
Yep. Okay, then I guess we'll wrap it up for now. So thank you very much for the talk. I think everyone enjoyed it greatly. And I think at least I think it's fantastic work. I hope a lot of people agree after this. I guess I'll reiterate that obviously if anyone has examples on which you would like to test this tactic, then it would be fantastic to actually collect as many of these as possible to make it as robust as possible. And yeah, thank you for the talk, and I'll stop the recording now.